Okay, guys, so if you guys are working on this on your own, then I guess I'll just talk to myself, but I'm going to go over it. This one is a bit of a trickier Hess's Law problem, but should be doable. It's very basic math still. So first thing we want to do is identify the reaction that we want. So this is the reaction that we want to end up with. And so let's start with CO2. We need to have CO2 on the left side of the equation, right? The reactant side. So we're going to look for the reaction with CO2. Looks like this third one right here has CO2. But if you guys notice, it has 2 moles of CO2, right? But here we only want 1. So we're going to have to use reaction 3, but we have to divide it by 2. So I'm going to divide CO2 by 2 to get just 1 mole. We're going to have to divide the 3. So unfortunately, we have to have a fraction here. So 3/2 H2O. Going to draw our arrow. We're going to have 1/2 a mole of C2H6. And then we're going to have to divide this by 2, which gets us the ugly 7/4 O2. And then that means for the enthalpy of the reaction, we'll also have to divide that by 2. Okay. So not the prettiest problem, but it will all work out at the very end. Okay. So far, so good? So we used reaction 3 right here. So I'm going to cross it out. I don't recommend you do, just so you have a reference copy. But I'm going to cross it out because we only use the reactions once. All right, now we got to go to the product side. So we have 1 mole of carbon on the product side. So reaction 2 has carbon on the product side. So we also need to divide this by 2. So we're going to have to divide C2H6. So 1/2 C2H6. Divide this by 2. That'll give us 1 mole of carbon plus 3/2 H2O. Oh, not H2O, my bad, H2. And then we'll have to divide the enthalpy by 2 as well. Okay, so far so good. I'll pause right there. If you guys have any questions at any point, please let me know. And just so we're clear, this part right here is talking about the enthalpies. And we're done with equation 2. Alrighty. So we have to have O2 on the product side as well. We already have O2. And so we just need to make sure everybody cancels out, right? So let's look right here. We don't want water, and so we can't cancel that out yet. That means we have to have water on the right side of the equation here, right? So if we look here, luckily we have water. But what's the problem with equation 1? Yeah, it's on the wrong side. It's on the reactant side. So we're going to have to flip this equation. So we're going to flip it so that we have H2 plus 1/2 O2. And we got to get water on the other side. So if we flip an equation, what happens to the enthalpy? Yeah, negative sign or opposite sign. Yeah, so it'd be negative 643. All right, so we're not done with equation 1 yet because if you look on this side, we have 1.5 moles of water, but we only have 1 mole right here, right? So what we're going to have to do is we're going to have to multiply this entire equation by 3/2. So 3/2. 3/2 times 1/2 will be 3/4. And then 3/2. And then obviously the enthalpy as well. Because we had 1/2 times 3/2, 3/4. Yeah. Yeah, make sure you guys ask me, because I know the math can get a little funky here with the fractions and everything, and I want to make sure we're all on the same page. So yeah, that's why we get 3/4 right here. Okay. All right. Any other questions? We're actually almost done now. Okay, so now we can start canceling stuff out. So again, we want to get rid of the water. So we got 3/2 water here, 3/2 water here. So these boys will cancel out. We don't want the C2H6, and we got half a mole on both sides. We also don't want the H2, so the H2 will cancel out, 3/2 on both sides. And then here, we have 3/4 and 7/4, and that's 4. And then if you subtract them, it'll be 4 over 4, which is going to be 1. So this will cancel out, and this will get us just to O2. So if we sum up this equation just to make sure we did everything right, we should end up with 1 mole of CO2, 1 mole of carbon, and 1 mole of O2. Okay, so we did everything right, and now we can just solve out this right here. Okay, so I will give you guys maybe about a minute to solve that out, but do you guys have any questions on any of the steps? This is about as hard as it's going to get on the AP test. Yeah. Usually you won't even see quarters, but this one has quarters, so it's pretty tricky. All right, so you should get a value of 886.35 kilojoules for your change in enthalpy. Okay. So hopefully that was helpful. I know I messed up the last time we did it. I actually posted an updated version of that problem if you guys want to take a look at it on Canvas. Alrighty. Any questions, guys? Chilling? Easy peasy now? All right, so that you can keep. You don't need to turn it in. And I know I was joking, but it's not a quiz. It's just for you guys to refer back to. It's a good practice problem too. Okay, so let's go back to our original notes now. Today we're gonna get started on section 8, which is enthalpies of formation. Okay. Enthalpies of formation. Let's see. Let's see. Where am I? Nope. Okay, there it is. Okay, so enthalpies of formation. So standard enthalpy of formation, this is the symbol right here, delta H, and then like 0 degrees, and then F as a subscript. Basically, it's the change in enthalpy that's needed for the formation of 1 mole of a substance from its most stable form of its constituent element. So kind of a long definition, but so an easy way I like to think of it is when you have elements in their standard state. Standard state is just basically how they're usually found in nature. That's probably the best way to think about it. When they react to form 1 mole of a substance, the change in enthalpy is called the standard enthalpy of formation. Okay. Okay, so that's basically what it means. When you have elements in their standard state and when they make 1 mole of a substance, that change in enthalpy is the enthalpy of formation. Yeah.
Sorry, do you mind explaining that?
Yeah. So I think it's best with an example. So let's actually go over example 1. So let's look at the formation of carbon dioxide. Carbon dioxide is made out of obviously carbon and oxygen, right? So this is what it's made. This is the formula for carbon dioxide. Now carbon is made out of carbon. So carbon's most stable form is a solid, and specifically solid graphite. Okay. And the oxygen in carbon, most stable form of oxygen is O2 gas. So the standard enthalpy of formation is basically if you reacted these two things together to make carbon dioxide, how much enthalpy, the enthalpy of that reaction. That's basically what it is. Okay. So when you have a molecule, basically if you react the most stable forms of the elements that make up that molecule, the change in enthalpy will be the enthalpy of formation. Okay. So we got another example here. So water, liquid water. H2O is made out of H and O, right? Most stable form of H is H2 gas. Most stable form is O2 gas. And since we're talking about making 1 mole of water, that's what standard enthalpy is. It's the formation of 1 mole. We have to use half a mole of oxygen, and the enthalpy of that reaction will be the standard heat of formation. Okay. Yes. Exactly. It has to be 1 mole of a substance. You can only have 1 mole of something on the product side. Yeah. Good point. Okay. All right. Any other questions about that? Does that conceptually make sense? Yeah. So you have to have exactly 1 mole of product on the right side. Okay, so one special case I do want to tell you about is what if you're making the most stable form of that molecule? So here, O2 is made out of only oxygen, right? The most stable form of oxygen is O2 gas. And so if you're trying to make or produce a molecule that's already the most stable form, the standard enthalpy of formation will always be 0. Okay. And if you want to find the enthalpies of formations of compounds, you can look at Appendix C of the textbook. You'll probably need to use that for your homework. No, you'll always be given it. Unless I am extending the test date, guys. I'm just kidding. Yeah.
Is it like for
every compound will have its own enthalpy of formation, and depending on the state of matter, it'll be different. Yeah, so solid water will be different than liquid water versus water vapor, or ice water and water vapor. Yeah.
Is it possible for us to calculate like in the equation what
Yes, next section. That's fun, guys. Isn't this very fun? Yeah. Depends on the reactants. Yeah, we'll do some practice problem, and you guys will see how to calculate it. Yeah, you guys are moving ahead of me. Okay, yeah. It does, but it's based on the reactants. You got to use the reactants to calculate it. Yeah, so it will have its own, but oh, I see what you mean. Yeah, so it will always be the same. Yeah, sorry, I misunderstood. Okay, so in your class workbook, you have this table. This is what we're gonna be using for our practice problems today. You guys don't need to copy it down or memorize it. I'll be honest, I don't have it memorized other than like, oxygen, hydrogen, carbon. But what I want you guys to do is just based on what you know about enthalpy of formation, I want you guys to take a look at 6.21. Okay, for 6.21, basically you're trying to answer, hey, which one of these, if any, does not represent a standard enthalpy of formation? Okay, so we have 3 chemical equations underneath, A, B, and C. And I want you to just analyze each one and try to figure out, hey, does this reaction represent a standard enthalpy of formation? And if it does not, how can you change it to make it into a standard enthalpy of formation? Okay. This part up here might be helpful. You might want to check it out, but yeah. All right, so I'll give you guys maybe about 3 minutes to try it out, and then we'll go over it together. So just see, do these 3 reactions, are they representing standard enthalpy of formation based on the definition we looked at? And if not, how can we change it to make it represent it? Okay, let's start with A. Okay, so A. Anyone want to bravely take a shot? Yes. Yes, it is yes. Why did you say yes? Educational guess. Yeah, anyone take a shot? Yeah. Yeah, that's one good thing that we can observe. It only forms 1 mole of the product. What else? What was that? Oh, okay. It looked right. Yeah, it is right. Good eye, guys. So yeah, one of the things you'll notice that you have only 1 mole of the product. If you look at oxygen, what's the most stable form of oxygen? O2 gas, right? And I didn't mention this earlier, but you guys may have been able to guess, sodium is a metal, right? Most stable form of a metal is a solid. And so, yeah, that one would be good. Okay. All right, so speaking of metals being solids when they're stable, what about B? What do you guys think? No, why? Yeah, first of all, it's making 2 moles of a product. So how can we change it? We can make it 1 mole. Yeah, dividing by half. What else? Exactly, yes. Potassium's a metal, right? So it should be a solid for the most stable form. So those are the 2 changes you would make. It has to be 1 mole of product, and potassium's a metal. Metals are most stable when they're solid. Yes, you want to try C?
Yeah.
Okay.
I think it is. I think it's yes.
Okay, why?
Because the right side is equating to, like, if you swap this, or I guess you'd have to swap the sides.
Yes, that's correct. You do need to swap it. So let's start with that. You do need to switch the reactant and product. So it's not correct, but you do want to swap it. Why do you want to swap it?
Because
1 mole of product. Yeah, Josie.
I don't think carbon is, well, it's diamond has a potential.
Wow, amazing. Yeah. So if you look at carbon, it's in diamond form, right? Diamond, it has an enthalpy of formation, which means that it's not the most stable form. We also talked about how carbon, it wants to be a solid graphite, right? And so one of the issues, like Robbie said, we first want to swap it because we need 1 mole of product, right? Here we have 3 different products with different moles. So we need 1 mole of product. Second, carbon should be solid graphite. Anything else? No, that's pretty much it. That's it. Alright, so that's enthalpy of formation. Hopefully that wasn't too bad. So yeah, just keep that in mind. Sometimes like diamonds are solids, but just because it's the same state of matter doesn't mean it's the most stable form. And that's the one they usually kind of throw as a curveball. It's the difference between graphite and diamond for carbon. So just keep that in mind. Okay. Yeah.
it does say solid.
C solid.
Yeah.
It should always specify whether it's graphite or diamond. Yeah. Okay, guys. Now, fun part. We are going to be using the compounds and their enthalpies of heat to calculate the enthalpy of the reaction. It's extremely fun. It's like a game. A very fun game. Okay. So I have this copied here for you. These are all the compounds that I believe we should need. But is that all of them? Do I have all of them in there? I think I have all of them. Okay. So when you calculate the enthalpy of a reaction, this is going to be the equation right here. Basically, this sigma, this Greek symbol right here, basically means sum of all. Okay, so if you want to find the enthalpy of a reaction, all you do is you calculate the total enthalpy of all the products, and you just subtract the enthalpy of the reactant. So pretty basic change in formula. Okay, so the enthalpy of a reaction will be equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Okay. Okay, there is one thing that's not on this table, but it was in our notes earlier, but I'll give it to you guys. The enthalpy of water, it's going to be negative 285.8. Okay. Yeah, so I'm gonna actually go over with you. If you guys feel confident doing it, you guys can. But I'm gonna go over step by step. Okay, so here we're gonna find the enthalpy of the reaction when you combust 1 mole of glucose. Okay, it's carbon dioxide and water. So we want to first find the sum of the enthalpy of the products, and then we can subtract it by the reactants. Okay, so let's start with the products. So for our products, we got CO2 and we got 6 moles of that, right? If we look on our table for the enthalpy of CO2, it's gonna be negative 393.5. So all we gotta do is 6 times negative 393.5. And then we're gonna add 6 moles of water, which is negative 285.8. So if you add those up, that will give you the enthalpy of the products. Okay. Pretty simple, right? Chem's easy, guys. Yeah, Chem's easy as much as I love chemistry. Okay, so once you guys calculate the sum of that, let's see. I should do it too. That way you guys can correct me if I'm wrong. Okay. I got negative 4,075. Woo. Yeah, you got that? Okay. Oof. I'm just making sure I'm getting it right. I got nervous after last time, guys. Oh, fool. Okay, then we got to do the reactant side, which is glucose. So glucose, if you look down here, has a enthalpy of negative 1273. And then we don't have the enthalpy for oxygen gas. What do you guys? Yes, it's 0. Why is it 0, Josie? Amazed. Amazed. Yes, it's in the most stable form, so it's 0. So yes. So if you ever see anything in its most stable form, oxygen gas, hydrogen gas, chlorine gas, solid carbon graphite, then it'll always be 0. Yes.
So for the problems on the test, I just gave every single
Yeah.
FOB.
You'll get this, yeah. Something like this. And if it's not on there, it's almost safe to assume that it's going to be the most stable form. Depends on the sign.
No, because you use the
So,
alpha,
yeah. So
minus and negative, it's positive.
you're getting ahead of me. I'm trying to plug in here. So we got negative 4,075.8 minus negative 1273. So if we do this, it's gonna be plus operation. Yeah, so negative times a negative. Josie, I was about to get to it.
No,
You
but I
spoiled
didn't
it.
know, okay?
You spoiled my opportunity to share that insight. No, I'm just kidding. That was a good observation. Yeah, so if it's negative times negative, so obviously it becomes positive. And so it will become less negative. And so, but the magnitude will decrease. And so it'll be negative 2802.8 kilojoules per mole. All right.
Wait, that's
So you guys didn't multiply it,
Mhm.
you're trying
Yeah.
So you're saying that magnitude decreased from
Magnitude decreases because the absolute value got smaller, but the enthalpy increased because it became less negative.
what you're saying, you're comparing the magnitude decrease to the reactants. You said it decreased, right? The magnitude decreased, but what did it decrease from? Like,
Decrease from the product. My bad. Product. Sorry. I shouldn't have used that term. Sorry. This is the answer. Yeah. Yes. Not necessarily.
So the magnitude is like the absolute value.
Yeah.
And then if you say like the enthalpy, it's like the positive.
Yeah, but usually when you're talking about enthalpy, you're talking about absolute values.
But
Just say the magnitude of the enthalpy increases or decreases if you ever need to communicate that. Yeah. Oh, we're getting all confused now. Any questions? Yeah. Because it's asking us for the reaction per mole of glucose. So it should be kilojoules per mole. Also, all these values right here, it's kilojoules per mole. So all these, yes, but all these numbers right here, we use kilojoules per mole. So this is the answer because we're looking for the combustion of 1 mole of glucose. So I guess if you want to specify, it'd be this per kilojoules per mole of glucose. Yeah. You still seem confused. Yeah, so if we just look at the problem, what it's asking us to find. It's asking us to find the delta H of the reaction for the combustion of 1 mole of glucose, right? So we're finding the enthalpy change when we combust this. That's what the question is asking us for. Yeah, so if you wanted to be more specific, it'd be kilojoules per mole of glucose. Yeah.
So for glucose, it's negative 1,200 to like create like that standard information. But it's negative 2,800.
Yeah, for mole of glucose combusted. Yeah, if you guys want to get more specific. Dang, you guys getting me down to the nitty gritty. You want me to put the E behind mole too? So you're sure? Oh wait, moles. Just kidding. No, but thank you for asking. These are good questions. Well, if it okay, that's if I do per 1 mole of glucose, but you can still say moles. Yeah. Okay, whatever. You know what? English my second language, okay? That's discriminating against me. I'm just kidding. No, you guys are right. Okay, let's go to 6.23. You guys think you could try this one on your own? Okay. So I'm gonna have you guys try 6.23 on your own. Now I want you guys to read this very carefully. This is for the combustion of 2 moles of ethanol. But the balanced reaction is just 1 mole. I know.
What?
Crazy. I'll give you guys about 4 minutes to try this out. In this problem, it's a little bit different because it's asking us for 2 moles of ethanol, okay? So it's a little bit different than regular standard heat of formation where it's just 1 mole. But it's not too bad. So there's 2 things we can do. First thing we could do is either you can just double the reaction if you wanted to. So you could either double the reaction or you can calculate it normally and at the very end just multiply it by 2. Either way, you're going to get the same answer. So I'm just going to multiply it by 2 at the very end just because numbers will be a little smaller. Okay, but let's find the products and the reactants, okay? So products, you got CO2, which is negative 393.5. So negative 393.5. There's 2 moles by 2. You're going to multiply that by water, which was 285.8 times 3. Okay, and again, if you did it by 4 and 6, that's fine. Okay, I'm just going to multiply by 2 at the very end. Okay, and so if you multiply together, sorry, I didn't do this yet. Unforgivable. Okay, you should get negative 1644. Maybe?
Yeah.
Okay, thank you. Gotta make sure, guys. Okay. We have ethanol right here. Ethanol is negative 277.7, and you only got the 1 mole. And then O2 is this most stable state, so it's 0. So for your final reaction, your delta H of the reaction is going to be negative 1644.4 minus negative 277.7. So basically, you just need to add 277.7, and you should get a final answer of 1366.7. And this is kilojoules per mole, so kilojoules per 1 mole. So if we want to find it for 2 moles, we're going to have to double that. And so we should get negative 2,733.4 per 2 moles. So there you go. Okay. All righty. A lot of math. All right. Any questions about that? Chilling? All righty, guys. So we're going to take a quick 5-minute break. If you guys need to go to the restroom, go to the restroom. If you need to stretch, get some stretch. But we're going to continue after 5 minutes. All right, guys. So we're going to move on to the next topic, which is called calorimetry. Okay. Okay. Next topic is calorimetry, and the reason why I extended the test is so that we can fit in a lab next time. Okay. So it's gonna be a calorimetry lab. So this is the content you'll need to know to do well on your lab. No fire. Oh, there's a hot plate though. Okay. So calorimetry. So calorimetry is the measurement of heat flow. So we talked about how heat is energy going from one object to another object. And so we measure heat flow using something called a calorimeter. Okay, now before we talk about what a calorimeter is, we are going to talk about why this works, how we can measure heat flow using, the chemical principles and the properties of things. Okay, so every single substance in the universe has something called a heat capacity. Okay, heat capacity, the technical definition is the amount of heat that's required to raise the temperature by 1 Kelvin or 1 degree Celsius. So basically, you guys know some things get hotter faster than other things, right? Like some people get madder than them. No, I'm just kidding. But things like metals, right? Metals get hot really, really fast, right? But things like water, it takes forever to boil, right? And so different substances have different amounts of energy they need to increase their temperature the same amount. Okay, that's what heat capacity is. Okay, now the way that we represent heat capacity in moles is C and then subscript M, Cm. That's the heat capacity of 1 mole. But typically, we're going to be using a value called specific heat capacity or specific heat. And it's the amount of heat needed to raise 1 gram of a substance by 1 degree Celsius. Okay. So I'll give you guys some time to copy down the equation below. I'll break down what everything means in a sec, but you're going to need to know that equation. And please don't play with scissors. It's scary. A good teacher would say because of your safety, but it's more for my safety. You never know. You never know. Do it. Do it. Throw the scissors at me. Do it. I will end your diploma. I will end your career. And I will laugh at you as I drive by on my motorcycle while you are begging for my mercy. And I'll spray water on you with a water bottle.
Or I'll be like working at the drive-through McDonald's.
Hey, that's a good job, man. Good benefits. I'm just gonna give you a hard time. I'll throw that drink back at you.
Okay, cancel.
I don't care. Cancel me. Everyone says that they're gonna cancel me for something I say. I'm like, dude, cancel me already. I should have been done canceled.
I've been
Oh yeah. Hey, and you're still here and you're doing fine.
That's true.
Yeah.
I'm still here. I'm still here, aren't I, Claudia?
Or barely. All right. Anyway, did you guys copy this equation down? Guys, you're gonna need this equation right here. No, take your time. 1 minute. Okay, so this equation basically means that the heat capacity, so the amount of heat energy it takes to raise the temperature of something, it's equal to the amount of heat, okay, divided by the grams and the temperature. So let's put the units of measurement in here. So heat is measured in joules or kilojoules. Oh man, I was like, guys, we've been using this unit like this entire unit. Okay, grams is grams, and then temperature changes, yeah, Kelvin or Celsius. Okay, good. So specific heat has a unit of measurement, either kilojoules or joules divided by grams and Kelvin or Celsius. Okay, so I want you guys to use what we just used right here, this equation, to solve out 6.24. And I want you to find the specific heat of water. You are not. You're a genius. You don't have to convert to kilojoules. Yeah, you can keep it joules. It's just heat. Unless you really want to give me the value in kilojoules.
No, I
Alrighty, guys. So if you guys are finishing up, please feel free to finish up, but let's start going over it. So what value should we plug in for Q? Yeah, 209 joules. Okay, what value for M? 50. Yeah, 50 grams. And then for the delta T, what's the change in temperature here? Yeah, just 1 Kelvin. Okay. So all you got to do is punch that into your calculator. Yeah, just double checking. 4.8 T. And it's going to be joules per gram degrees Celsius. Or Kelvin. My bad, Kelvin. Kelvin. You guys are going to be all up in my case again about the letters. So that is the specific heat of water. So in order to raise 1 gram of water by 1 degree Celsius or Kelvin, it's going to take 4.18 joules of energy. Yeah. You're going to see this number a lot, and so you'll get used to it. Okay, everyone got that written down? Because you're going to need it for the next problem. Okay, so with that being said, I want you guys to use the same equation. Whoa, where did I go? What's this? Oh, sorry. I gotta mention something, sorry. Okay, so specific heat of water was 4.18, right? Now, the reason why we calculated that is let's compare it to some other substances. So water's 4.18, nitrogen gas 1.04, aluminum 0.9, iron 0.45. So looking at all these different substances in water, what do you notice about the specific heat of water? It's very high, which means it takes a butt ton of energy to heat up water. So water takes a lot of energy in order to heat up. That's why it takes forever to boil water for your ramen noodles.
Why did you decide to use water?
Because we are made of 80% water.
Oh,
That's why it's a little important. Okay. You want to use acetone for your ramen noodles? All right, man.
quicker.
Well, I mean, yeah, it'll make something else quicker too. Okay, so death, yeah. So we can rearrange the specific heat equation to find heat flow. So a lot of times we're not going to use the specific heat equation. Instead, we're going to turn it into a heat equation, heat flow equation by doing this. We can rearrange the equation to multiply the specific heat of something times mass times the change in temperature. Are you doing arts and crafts right now? No, you're good. I don't want it. So Celsius and Kelvin, when you're talking about change in temperature, is the same. Yeah, so you can do Kelvin or Celsius. Yeah. Okay. Yeah. So this allows us, basically this equation allows us to calculate how much heat something needs to gain or lose using a specific heat. Okay, so with that being said, let's use that equation we just rearranged. Q equals Cm delta T. And I want you guys to calculate how much heat it takes to warm 1,000 grams of water from 22 degrees Celsius to 98 degrees Celsius. Okay, so I'll give you guys about 2 minutes to do that. You're going to need the specific heat of water that we calculated in 6.24. And then after that, we'll move on. Okay, so for heat, let's plug in our values. So we're talking about water. So we know the specific heat of water as 4.18. And that's going to be joules per gram. And then either Kelvin or degrees Celsius, doesn't matter. Okay. The mass of water here is 1,000 grams. Now for delta T, since we're talking about change, we don't have to convert because the change between Kelvin and temperature is going to be exactly the same because it's the change is through addition. Okay, so if you wanted to really change it to Kelvin, you can, but you're doing extra work because the change is still going to be the same. Okay. All right, so you plug all that into your calculator, you should get a final answer of 317,680 joules. And if you really wanted to do it in kilojoules, which you don't have to, is 317.380 kilojoules. Same thing though. Yes.
Why wouldn't we?
Yeah, because it's gonna give you the same value. The change is gonna be the same. So if we do 98 minus 22, that's 76, right?
Yeah.
Let's convert everything to Kelvin though. So if we convert it to Kelvin, this will be 295 and then 371. If you do 371 minus 295, it's still 76. So it's gonna be the same when you do the change. Now, if we're talking about the temperature itself, then we have to convert to Kelvin. But whenever we're talking about the change in temperature, it's gonna be the same value between Kelvin and Celsius. Yeah. Any questions?
Cool.
Alrighty, guys. So now we're gonna talk. Now that we know how to calculate heat flow, we are gonna talk about the part that we're gonna be doing for the lab. We are gonna be doing something called calorimetry. Now, calorimetry, we need to use a very advanced, sophisticated piece of technology called the styrofoam cup, which you guys have in front of you, and I'm gonna teach you guys how to make a calorimeter. Okay. Okay. So here, we're going to be mixing 50 milliliters of 2 molar hydrochloric and 2 milliliters of sodium hydroxide in a coffee cup calorimeter. So basically, let's draw the calorimeter on for our problem, okay? So amazing. Beautiful drawing. Thank you, but I know you're full of it. Okay, so inside of the calorimeter, okay, we are going to be reacting hydrochloric acid and sodium hydroxide. Okay. Now it tells us that the temperature increases from 21 degrees Celsius to 30 degrees Celsius. So what's the delta T? 9. Yeah. So the delta T is 9. My bad. I did that in my head and it just came out. Okay, so 9 degrees Celsius. Okay, the combined solution has a total volume of 100 milliliters, density of 1 gram per milliliter, and a specific heat of 4.18 joules per. Basically, it's water. Okay, so we drew a picture of the system. We did part A. Congratulations, guys. Amazing work. Beautiful. I'm so proud of you guys. Okay, so now what we're going to be doing is we're going to be calculating the enthalpy change for this reaction in kilojoules per mole of HCl, assuming that you don't lose any heat in the calorimeter, because that advanced piece of technology in front of you will not lose any heat. All right, so you're probably like, what the heck am I doing here? So first thing we want to do for part B is we want to write the chemical equation. Okay, so we got HCl. Okay, and we're going to be reacting it with sodium hydroxide. Okay. All right, so because you guys are experts at these ionic equations, okay, what is one of the products that we make? Yeah, H2O. So proud. And then the other one? NaCl. Table salt. Oh. I'm gonna sabotage your score. I'm gonna find a way. I'm gonna find a way to grade it myself. All right, all good? Okay, so we got our balanced chemical equation, and now we got to use some info from the problem in order to work on this. So it tells us the molarity and the volume of the acid and the base. So we got 2 molarity HCl, and we got 50 milliliters of HCl, and then we have 1 molarity sodium hydroxide, and then we got 50 milliliters of sodium hydroxide. Okay. So far, so good. You guys good? Okay. Now we want to find heat flow, obviously, because we're using the calorimeter. So we can just copy that down. Q is C M delta T. Okay, and now we just need to plug in the values that we need into this equation, okay? Now, fortunately, it gives us most of the info. Okay. So for C, what is the specific heat? Yeah, specific heat of this reaction right here is 4.18 joules per gram Kelvin. Okay. Now, mass is the one that we need to calculate, right? Because we're trying to find the mass of the solution that's in here. So fortunately, we have a nice little conversion here. We have 100 milliliters of solution, and then it tells us the density, right? So if we multiply by the density, 1 gram per milliliter, what's the total mass? Yeah, 100 grams. That's going to be our mass. Okay. So that's what's in there. And then obviously delta T is 9 degrees Celsius. All right, so if we calculate all that out, we get 3,762 joules. Now, this is not our final answer because it's asking us for joules per mole of HCl, right? But if we look at this, we can automatically tell just by the molarity formula, this isn't going to be 1 mole of HCl, right? No, because this is just for everything here, this whole reaction. So what we got to do is we need to take this information about HCl and we got to find out how many moles this is. So we know the molarity formula is moles over liters. So let's just substitute some things. We got to convert 50 mils to liters. So if we convert it to liters, it'll be 0.05 liters. Molarity is 2 molarity. Okay. So this is going to give us 0.1 moles of, 0.1 moles of HCl. Okay. So far, so good. So now we have everything that we need in order to find the enthalpy change of the reaction per kilojoule or kilojoules per mole of HCl. We got joules here, so let's convert that to kilojoules. So that'll be 3.762 kilojoules divided by the moles that we use in the reaction per 0.1 moles of HCl. And then that will give us our final answer of 37.62 kilojoules per mole of HCl. There you go. That's your final answer. Yes. It's just what's given to you right here, the specific heat. Yeah. No, all good. I converted joules to kilojoules. Yeah, 3 times to the left. 100 grams of the solution, the entire solution. Yeah, because that's what changes. That's what tells you about the heat flow. Yeah. All right, so that's an easy calorimetry problem, guys. So next time when we meet, we will do the one that we will do an example like the one you're going to be doing in the lab on Friday after the test. And so, yeah, don't worry, we'll get more practice in. We have a lot of time left to just do calorimetry and one last topic. And yeah, so we should have a lot of time next time to prep for the test. Again, test on Friday. We'll do the lab right after the test, and it's going to be on calorimetry. So if you want to leave your calorimeters here, you can just leave it up here. Just make sure you write your name on it. If you want to take it and decorate it, that's great. Just make sure you have it on Friday to do the lab, okay? Other than that, we're all good, guys. You guys can start packing up. Good job today.